Right. Okay. Let's start. Thank you, everyone, for coming to today's colloquium. And it is my great pleasure to introduce today's speaker, Professor Bruce Gaulin from McMaster University. And Bruce. Okay. So now it's official. So Bruce received his PhD degree from McMaster University. And then I think he went to Oak Ridge and then came back to McMaster to take up the faculty position. And he's been there ever since. I won't tell what year he started. And then he has done pioneering work on spin ice first, and then classical spin ice, and then now he's working on this very interesting project on quantum spin ice, which is drawing a lot of attention, including many people in our department. So he will tell us about his recent research on the quantum spin ice. But I also have to mention that Bruce has been sort of playing a very important role in the Canadian physics community for his leadership role as physics as well as neutron scattering. So I remember, I guess Bruce often actually talks about sort of his experience in the 80s when he was working with some other people like Tom Mason and Chichan Kao and Dune Gibbs. And so of these four people, I think Bruce kind of jokes that three other than Bruce actually became the national lab directors in the US and so on. And when I hear that story always, I felt like that's sort of a wrong characterization because all four of those people became leaders in the physics and neutron scattering community because Bruce definitely has been playing a very important leadership role in Canada as a president for Canadian Association for Physicists and also the president of Neutron Scattering Society of America, and so on. He has been really instrumental, especially for neutron scattering community in Canada. That's sort of really the leader in this field. They said we as a community owe a lot to Bruce. So I wanted to say that to Bruce when introducing him. So with that, I think back to physics. I think he will tell us about very interesting development in quantum spin ice. Bruce.
Hey. Thanks very much, Young Jun, for that very kind introduction, and also thank you for not saying what year I started at McMaster at. I would just say that I've been around long enough that I've had the pleasure of interacting with at least two generations of University of Toronto professors. So the current generation I have close contacts with. The previous generation, I also had very close contacts with, and I'm a great admirer of this institution, and I'm very happy to be here today. Okay, so I'm going to be talking about work on a particular problem that's known as spin ice and quantum spin ice. And by the way, I don't normally come up with these sorts of subtitles, which were meant to be whimsical, but actually those were the instructions from the Colloquium invitation. So, I did my best, right? So keep that in mind. So this work I'm going to be telling you about is work that was carried out over about a 7-year period, 6 or 7 year period. And it involves, several complementary sets of expertise. And of course, these don't reside with any one person. So after 7 years, I've got quite a large number of collaborators. And the collaborators, well, some of them are people from my group at McMaster and some colleagues at McMaster. Some of them are theorists, like this group here from MPI Dresden. And some of them are material science specialists, so specialists in synthesizing new materials, growing new materials. Some of them do the actual low temperature physics experiments. And as I say, some of them produce the sophisticated theory that we use to model the experiments with. So the net result is that after 7 years, you've got a fair number of collaborators. And so I'm going to be talking to you about materials with what I'm going to call exotic magnetic ground states and quantum disordered ground states. But to set the stage, I should probably back off and tell you that almost all materials that you'll ever interact with actually have ordered states at low temperatures, right? They're crystalline ordered, they have translational symmetry, or they're magnetically ordered, or they might even be electronically ordered, as in superconducting type ground states. And so what usually happens in most materials is that at sufficiently high temperatures, there's some sort of entropy-dominated disordered state. And at sufficiently low temperatures, there's some sort of energy-dominated ordered state. Okay? And magnetic materials have been, probably the playground to understand, what happens as a system goes from the disordered state to the ordered state through a phase transition. And this is what happens, as I say, in most magnetic materials, and it's what happens in most materials, period. But in magnetism, you have actually a very simple model for understanding what's going on, that you have local dipole magnetic moments that are arranged on a lattice in a material. And those dipole magnetic moments, you can think of them as little vectors, little spins. And there'll be some relatively simple Hamiltonian like this one, which is referred to as the Heisenberg Hamiltonian, that describes the energy difference between having the spins point parallel to each other and anti-parallel to each other as nearest neighbors. And so, if the sign out front here is such that the energy can be lowered by having the spins point parallel to each other, this gives you a ferromagnetism. And so, all the spins will tend to point in the same direction. That's actually, even though that's the basis for all sorts of technology, and we've known about it for thousands of years, it's actually not the most common form of magnetism. The most common form of magnetism is antiferromagnetism over here, where the tendency is to have the dipole magnetic moments arrange themselves anti-parallel to each other. Okay, and that you get just by flipping the sign of the J constant out front. And actually, what's shown at the top here is a two-dimensional real space realization of this sort of problem. These are actually classical Monte Carlo results that are shown here. And in this case, you can have a given black square. A little black square would be an upspin, and a white square would be a downspin, for example. And you can see when you're above the phase transition, there's as much black as white, and it's not completely disordered, but it's largely disordered, right? You can see that there aren't correlations greater than about this sort of length scale here. But then when you go to low temperatures, you break symmetry between the upspins and the downspins. There's nothing in the problem that told you to do that, okay? The problem would be just as happy if you'd minimize the energy by having all spins up as all spins down, but you'll break symmetry, and you'll say have little islands of downspins coexisting in a sea of upspins, for example, at low temperatures. So this is what almost always happens. And what I'm going to tell you is that I've dedicated most of the last 35 years to looking for materials in which this doesn't happen. Okay, so we're trying to get this to not happen, and we're trying to preserve this entropy-dominated state to low temperatures. And the main reason, at least experimentally, for wanting to do this is that it precludes the conventional from happening. And if you preclude the conventional from happening, you at least open the possibility for unconventional phenomenology to occur. So then the question is, how do you do that? And there's a number of different ways to do that. But the way that I'm going to talk about, and actually the main way that is employed, is to get those interactions, so that is the tendency for spins to align parallel or anti-parallel, to work against each other, right? So that it's hard for energy to win over entropy. And you can do this with certain geometrical constraints. I'll show first how you do this in 2 dimensions with triangles. And then what I'm really going to be talking about is how you do it in 3 dimensions with tetrahedra. So, triangular architectures are very common in nature. You can have a 2-dimensional net that's made up of, tiling 2 dimensions with edge-sharing triangles, and that forms the triangular lattice, very common in nature. It's the basal plane of all hexagonal crystals, okay? Something that's less common in nature, but still not uncommon, is a network of corner-sharing triangles, and that's referred to as the Kagame lattice, okay? And both of these are networks of interconnected triangles, and so if we decorate a single triangle with classical magnetic dipoles that are antiferromagnetically coupled, we would like to form, we would minimize the energy by forming antiferromagnetic correlations on each side, okay? On each side of the triangle. And okay, I think that's probably good enough. We can keep going. Well, maybe not. Yeah. Yeah. Okay. Yeah. No, I'm just going to be bloody-minded and leave it up for another 30 seconds. Yeah. Okay. So yeah. So if you look at, say, a single tetrahedron, we're going to take a single tetrahedron and decorate it with dipole magnetic moments that are going to sit at the vertices with antiferromagnetic interactions between them. And so to lower their energy, they'd like to form this up-down pair on every side of the triangle. But of course, they can't do that on all three sides of the triangle. You can do it on two sides. You can have two sets of satisfied bonds, but you'll always get the third side having ferromagnetic correlations. So for every triangle, there'll be a degeneracy of 3 associated where you put the frustrated bond, right? You can put it on any of these 3 sides. So there's a degeneracy of 3 associated with one of the triangles. And then if you tile two-dimensional space by connecting up the triangles in either of these two motifs, you end up with a degeneracy that will scale with the system size, okay? And it'll scale actually very quickly with the system size. And this will lead to what's referred to as an extensive degeneracy. And an extensive degeneracy is sufficient to generate enough entropy to preclude the formation of an ordered state at low temperatures, okay? So the tetrahedron is to 3 dimensions what a triangle is to 2 dimensions. And so you can also form networks of corner and edge sharing tetrahedra that fill up 3-dimensional space. And so this is what you get if you connect tetrahedra together in this corner sharing motif. And this is referred to as the pyrochlore lattice, very common in nature. So again, let's start with a single building block, a single tetrahedron, and we're going to decorate this with, again, magnetic dipole moments. Okay, I'm going to describe what might sound like a somewhat contrived problem, but I'm going to have the magnetic dipole moments interact ferromagnetically with respect to each other, which means that they would actually like to all point in the same direction. Okay, but the magnetic moments are going to have an easy axis, and the easy axis for the 4 vertices of the tetrahedron are not collinear with respect to each other. So the easy axis for these dipole moments points directly into or out of the tetrahedra, and they're pointing in 4 different directions for the 4 vertices on the tetrahedron. So the system would like to form a ferromagnet. If you like, it's almost a ferromagnet, but this single ion anisotropy is precluding the moments from pointing all in the same direction. Okay? So you do get a net magnetization, and it's pointing from left to right over here. So there's a net magnetization going in this direction, but it's not the magnetization of 4 times the individual magnetization of the dipole moments, because they're not, they're constrained to not point in the same direction. Okay, so once again, there's a degeneracy for how you arrange the moments which will satisfy the low energy state for one tetrahedron. That you need to have 2 spins point into the tetrahedra and 2 spins point out of the tetrahedra. And you could convince yourself pretty quickly that there's 6 ways to do that for any one tetrahedra, and then a tetrahedron. And then if you join the tetrahedra together in this corner sharing motif to fill 3-dimensional space, you'll get, again, an extensive degeneracy, a degeneracy that grows so fast with system size that entropically you just cannot form an ordered state at low temperatures. Okay? And this is known as the spin ice problem. Okay, it's the problem that you get with ferromagnetic interactions and magnetic dipoles, where the local Ising-like anisotropy, gives you the 6-fold degeneracy on a single tetrahedron. And this was the discovery paper that's associated with this sort of problem. And as you can see, it's about 25 years old or so. And it's also one of the great branding exercises in all of physics in my career. That spin ice is a sort of term that people who know nothing about spin ice actually like to say spin ice, right? It's an appealing terminology. It's appeared on the Big Bang Theory, and anyway, it's been a great selling point, and it means something. Okay, so there's a reason it's called spin ice, and the reason it's called spin ice is because the degeneracy associated with these spins, on a tetrahedra, okay, is the same degeneracy that you find with the disorder associated with protons in water ice. Okay, so some people know, but not everyone knows, that the ice that floats around in your drink and the ice that you skate on, it's not actually an ordered solid. Okay, although if you've ever fallen on ice, you know that there's something ordered about it. Okay, and what's ordered about it is the position of the oxygens. Okay, the oxygens are all, they form a regular 3-dimensional crystal structure. Actually, there's many crystal structures for ice, right? There's like 14 different phases, but a lot of them have the protons that are part of H2O are disordered. And the way they are disordered is that they have a local rule, which is that the oxygens order and the protons have to arrange themselves so that it looks like every oxygen is in the middle of a water molecule. And that's the only constraint on the structure, and there are many, many ways to do that so that protons are not ordered. So that's why this is called the spin ice problem. And like I said, it's a very, very good branding exercise. Okay, and as I said, it was discovered in 1997, and actually not long after this, beginning in about 2004, people, and by people I mean theorists, started to think seriously about a quantum version of this problem. So everything that I told you about here, was completely classical, right? I mean, I'm drawing little vectors for the magnetic dipole moments. There's nothing quantum mechanical about this. But it didn't take long for theorists to start thinking about, well, what if we did treat the entities not as little arrows, but as operators, and we had an appropriate quantum mechanical Hamiltonian. And that was developed actually in a whole series of papers, and I'm sure I haven't referenced them all correctly, but there's one that's particularly relevant to this audience, which is this one in 2008, Banerjee et al. So this is from Young-Baek Kim's early group, which is actually quite famous now. Okay, and actually, in some sense, the the simplest explanation of what you get in the quantum version of spin ice that you didn't have in the classical version of spin ice is it introduces the possibility that you could tunnel between equivalent but different ground states of the system. Okay? So you can imagine that you have little pieces of spin ice. So these are little pieces of the corner-sharing tetrahedra. It's 4 of them. Okay? Both of them are in their ground state. So for both of them, if you look carefully, and I'm not really going to give you enough time to do that, but every tetrahedron has 2 spins point in and 2 spins point out. That's true for both of these tetrahedra. The difference between them is that this hexagon of spins that connects 3 of the 4 tetrahedra, they get flipped as you go from the left-hand side to the right-hand side. Okay, so these are both in their ground state, but you can induce transitions between them, which is basically tunneling between these different equivalent spin ice ground states. And what was realized almost right away, in fact, in this series of papers, is that this problem of quantum spin ice actually maps on to the problem of quantum electrodynamics. Okay, there's an emergent quantum electrodynamics associated with this problem. I'm not going to go into this in any real detail, but I would just say that one of the consequences, or one of the most intriguing consequences of this is that the excitation spectrum, so the excitations out of the ground state of quantum spin ice, are not conventional spin waves, which are the excitations out of the ground state of an ordered magnet. They're not conventional spin waves, but there's actually 2 sets of gapped excitations, which are referred to as magnetic monopoles, and either bosons or electric monopoles. And then there's a set of gapless emergent photon excitations. So there's an actual speed of light associated with the excitations in quantum spin ice. Okay, and at any rate, so the fact that there's an entirely different set of elementary excitations with very different properties from what we're used to in conventional ordered magnetic materials has generated a lot of interest associated with them. Okay, so I'm going to be talking about the experimental side of the problem and how we've gone about trying to identify materials which might be a candidate for quantum spin ice. And so about half of my research program at McMaster is material synthesis and crystal growth, and half of it is neutron scattering and low temperature characterization. So in terms of making materials, we're going to, of course, our palette is the periodic table, and we're going to focus on a family of materials. These are, it's actually a very large family of materials. So these are referred to as cubic pyrochlores that I mentioned before. They have the chemical composition A2B2O7. And this isn't the only way to form them, but it's very common to have the A site be a trivalent rare earth ion, and it can be almost any of the rare earth series here. A trivalent rare earth ion. The B ion is a tetravalent transition metal ion, and this isn't the only choice, but the one I'm going to talk about is zirconium 4+. So zirconium 4+, 1, 2, 3, 4, it has a krypton, filled shell electronic configuration. So there's only filled orbitals or unfilled orbitals. There's nothing else. There's no degrees of freedom to think about. The only degrees of freedom are associated with the cerium 3+, and 3+ means that we have 1 electron in the 4f shell. Okay. And so there is a partially filled orbital here. It's the 4f orbital. And if we apply Hund's rules to work out, the total spin angular momentum, the total orbital angular momentum, and the total angular momentum, right? If we work that out using, atomic physics, we'll determine that the total angular momentum is 5/2. That's associated with the ground state of cerium 3+. Now, we're looking for quantum spin ice, so we're looking for some sort of magnetic material which is based on some quantum number that is small, preferably equal to 1/2. And J equals 5/2 is not that small, right? But I'll show you in a few minutes that there are other effects that I haven't talked about yet that will take this J equals 5/2 and make it into an effective J equals 1/2. And then that's going to be the basis for our quantum spin ice. Okay. So anyway, I just say that there are literally hundreds of these materials, and you can put many different rare earth ions in the A site, and there's a very large number of different types of magnetic materials and non-magnetic materials that can form, and so nature really likes this particular structure. Anyway, I'm just going to be talking about this one example because it's an example that will eventually get us to something that looks like quantum spin ice. So one of the main features that we're looking for initially in candidates for quantum spin ice is evidence of no phase transition as you lower the temperature. So we don't want the system to order, we don't want it to freeze, we don't want it to do anything, right? We want it to sort of stay in what's basically its high temperature disordered state to low temperatures. So we eventually made cerium zirconate in single crystal form. And this is some of our initial characterization. This is magnetic susceptibility as a function of temperature. This is heat capacity as a function of temperature. And the only thing I really want you to take away from this is that these are smooth lines as a function of temperature. Okay, there's no sharp features. There's nothing indicating that there's a phase transition. In fact, this inverse susceptibility that has this curved, downward curved form as a function of temperature, it can be completely described by the red line that you can see there, which is known as the Van Vleck susceptibility. And the Van Vleck susceptibility requires that you know all of the wave functions and all of the energy splittings associated with that J equals 5/2. And I'm going to show you those in a second. So just suffice it to say that once we know those, you can calculate this using this expression, and you can describe the susceptibility completely. And there's no evidence for a phase transition there. For the heat capacity, you can see there's what's referred to as a Schottky anomaly around 100 millikelvin in this material, which you pretty much have to have because the heat capacity has to go to 0 at 0 temperature. Okay, but again, there's no sharp feature. There's nothing that looks like a phase transition. And actually, I'm actually overplotting our work on cerium zirconate with work done by a competing group. And this is a rather hot topic and has been for a while. And even though you might think you're working on your own brilliant idea in isolation, in fact, there's 3 or 4 different groups around the world who are doing almost exactly what you're doing. And at any rate, so this is one of those groups, and they published immediately after us, within a couple of weeks, literally. And I was kind of amazed at how well their results overlapped with our results, actually. So I've plotted them without doing, there's no manipulation. So actually, I'm sort of rather pleased with that. These are the 2 papers here. Anyway, no evidence for a phase transition. Okay, and so now we're going to get to the neutron spectroscopy characterization of this material. And I'm going to show you neutron spectroscopy on 3 different energy scales. And actually, that's often an important thing to do because there are 3 important energy scales in the study of basically any magnetic insulator. Okay, and these are spin orbit coupling, crystal field effects. Okay, and I'm going to explain both of these, and then exchange interactions, which are those interactions that tell you whether the spins want to be parallel to each other, ferromagnetic, or anti-parallel to each other. Okay, so condensed matter physics is low energy physics. And in the end, we're mostly interested in this energy scale here, okay? And we're going to get to that. But before we get to that and can make sense of that, we're going to have to understand what I would call the high energy physics of the problem, okay? And as I said, the high energy physics is spin orbit coupling and crystal field effects. So spin orbit coupling in insulators comes about because you have spins on electrons. So let's imagine a spin on a single electron, which is undergoing some sort of quasi-planetary orbit around a positively charged nucleus. And this is sometimes described as a relativistic effect, but it's a bit of a misnomer. But nonetheless, if we place ourselves in the rest frame of the electron sees the positively charged nucleus going around it, okay? And the positively charged nucleus is positively charged, right? So you've got a current going around the spin of the electron, and that produces a magnetic field, which then couples to the spin of the electron, and that's spin-orbit coupling, okay? And that is a stronger and stronger effect as you go to the bottom of the periodic table, because that's where the charge of the nucleus gets large, okay? So that's spin-orbit coupling, and in the problem that I'm going to describe, the energy scale for that is about 250 millielectron volts, okay? Nonetheless, this is the energy scale that separates the Hund's rule ground state, which is J equals 5/2, from the next excited Hund's rule state, which is J equals 7/2. There's 250 millielectron volts between there, okay? Then the next effect will be what are referred to as crystal field effects, okay? And the crystal field effects are due to the fact that the cerium ion is not in a vacuum, it's not in outer space, it's sitting in this solid, and 2 or 3 angstroms away from the solid, there are these electronegative oxygen ions. So the electric field at the position of the cerium is 0, but the electric field gradients are very large, okay? And those effects are strong enough to take the 6 states, so this is J equals 5/2, so there's 2J plus 1 fold degenerate. So there's 6 states, and it'll split them up into 3 states, 3 sets of doublets. And those will be separated by about 50 MeV each, okay? And so, as I said, we are low energy physicists, we are low temperature physicists. I'm not going to show you any data above 10 Kelvin for the rest of the talk, okay? So 600 Kelvin, 55 MeV, it might as well be infinity. So we're not going to care about these states, okay? And the only thing we're going to care about is, what makes up the ground state here, okay? And so that's what's going to give us our spin-1/2 degree of freedom, the fact that there's this isolated doublet, okay? And then these isolated doublets on different sites are going to start to interact with each other by these interactions, which give you ferromagnetism or antiferromagnetism. And if this was conventionally ordered, that would then give you a spin wave band and with an interaction of about 1 MeV. So this is what goes on in all magnetic insulators. But what's nice about these magnetic insulators, rare earth magnetic insulators, is that the energy scales separate out. So it doesn't have to be like this. But if the energy scales separate out, I find it easy to think about the problems in 3 separate problems, and we solve them sort of in order, okay? If they were mixed up, if 2 of them were the same, or if all 3 of them were same, it would be more confusing, but you could still do it, right? So at any rate, that makes this pretty easy. So I'm just going to show you some of this high energy spectroscopy. So this is our neutron spectroscopy. This is our really high energy spectroscopy with energies of 1/2 an eV. And you can see that there are some features here at low energy rather, which we're going to focus on later. But there's also this very faint line at about 250 MeV. This is actually the splitting between the J equals 5/2 ground state and the J equals 7/2 Hund's rule ground state. So we can study that if we want. Then we can go to a lower energy scale, say 150 MeV, okay? And now we're looking at the splitting between the 2J plus 1, 6-fold degenerate, Hund's rule ground state. It's going to get split up because the cerium is not in isolation. It's feeling this very electronegative environment from the oxygens. That's the crystal field effect, okay? And that will produce a splitting such that we have a ground state doublet and 2 excited state doublets. And this is an eigenvalue problem. And you can pretty much read off the eigenvalues from the data, because there's a magnetic excitation here, and there's a magnetic excitation here, and you only expect 2 out of the ground state. So the eigenvalue part of the problem is solved. The eigenvectors, which are the wave functions, you get by actually modeling how much intensity goes into the first transition compared to the second transition, and cross-reference that with the Van Vleck susceptibility, which depends on these answers, okay? Anyway, all of that can be done. The eigenvalue problem can be solved. You could probably solve it, given half hour or so. And at any rate, so the net result of that is that we understand the energy splitting and we understand the wave function that makes up the ground state doublet. And the thing that's interesting about the wave function that makes up this ground state doublet, okay, is that it has a very simple form. It's J equals 5/2, but Mj, so the Z component of J, is plus or minus 3/2 only. Okay, very simple, very clean wave function associated with that. So what does that mean? Whoops. And I don't know what's happened. Oh, okay. So did I hit the wrong button?
Yeah, it's okay.
Okay.
I don't know how you-
Okay. Right. So we're going to forget about all the excited states. We're only going to concentrate on the two states that make up that crystal field ground state. And we know their wave function. Okay. And this is their wave function. So we've got this big gap. So once we've got a big enough gap and we're at low enough temperatures, we don't care about anything above it. We only care about these two states. So there's a pseudo spin a half degree of freedom because there's two of them. So this is similar to, but different from, a real spin a half degree of freedom. So a real spin a half degree of freedom would be the spin of an electron, for example. And in that case, for real spin a half, we would have S equals a half, and the Z component of S would either be plus or minus a half. So this real spin a half has spin operators, X, Y, and Z spin operators, all of which behave like magnetic dipoles because this is a real magnetic dipole. And what that means is that if I look at the expectation value of Sz within these states, within either of these states, I'll get a non-zero number. Okay, that means that the Z component of spin is a dipole, and I can look at transitions between these two states that make up the ground state doublet. And the transitions between them are transitions that go between ms equals minus a half and ms equals plus a half. So that's an S plus operator or an S minus operator to go in the other direction. Okay, so it's a single S plus operator or S minus operator that connects those two states. Connecting those two states for the lattice gives you the spin waves. So you get conventional dipolar spin waves. Anyway, this real spin a half has X, Y, and Z components of the spin operators that all behave like dipoles. That's not going to be true for our pseudo spin a half here. Actually, the first part of that argument is the same, that if I took the expectation value of Jz within the states that make up this ground state doublet, I also get a non-zero expectation value. So the Z component of J behaves like a dipole, okay? But the X and Y components of J will not. And the reason they don't is because the two states that make up the ground state doublet, they're Mj equals, say, minus 3/2 and plus 3/2. And to get from minus 3/2 to plus 3/2, it doesn't take one raising operator, it takes three raising operators. So if one raising operator has a dipole character, then three actually has an octupole character. Two would have a quadrupole character. Okay? So the net result of all this is that for our pseudo spin a half degree of freedom, the different components of these operators, there's a dipolar moment associated with the Z component of spin, but there are octupolar moments associated with the X and Y components of spin. Okay? And it's a little bit more complicated than that. And that is that if you looked at these either octupolar or magnetic or dipolar magnetic moments in real space, and you looked at how they transformed under the operations, the point group operations for the cerium site. Okay, so that's the symmetry operations associated with this particular site here, which basically are a threefold rotation axis and a mirror plane. Okay, and you combine that with time reversal symmetry, you'd find that the Z component of pseudospin has dipolar symmetry. The Y component of pseudospin has octupolar symmetry, but the X component of pseudospin carries an octupolar moment but has dipolar symmetry. Okay, I can explain that to you in more detail if you like, but I don't have time to do it now. Okay, but just take my word for it for the time being. So this is the way we're going to think about the Z component of the pseudospin in real space, and this is how we're going to think about the X and Y components of pseudospin. Okay, and as I said, the X and Y components of pseudospin, they carry an octupolar moment. Z carries a dipolar moment. Okay, so you might think that I should be representing Sx and Sy by these things with 8 lobes, which look more like what you might have had in mind for an octupolar moment. But actually, we can make them up out of any of these L equals 3 orbitals. And the ones that I'm going to choose to make up X and Y out of are these two here. And the reason I'm choosing these is that these have the point group symmetry of the cerium site. They've got the threefold rotation about the z-axis. And they're related to each other by simply a rotation of 90 degrees about the z-axis. So that's why they're X and Y. Okay. Anyway, all of that is part of an argument as to, what is the most general form of the Hamiltonian that would describe the exchange interactions between these degrees of freedom, these pseudo-spin-a-half degrees of freedom. And you can see that, basically we get a term, most of this is a term that looks a lot like a Heisenberg exchange interaction. It looks a lot like the Hamiltonian that I showed you on the second slide, except for the coupling between the X degrees of freedom is independent of the coupling between the Y degrees of freedom, which is independent between coupling of the Z degrees of freedom, because they're all a little bit different, right? Z carries a dipole moment and transforms like a dipole. Y carries an octupolar moment and transforms like an octupole, and X carries an octupolar moment and transforms like a dipole. Okay, so actually X and Z have the same symmetry. Okay, they have this dipolar symmetry. So we're also allowed to have a term that couples those two, but we can't couple anything to Sy. Okay, so this is the most general form of this Hamiltonian, and the theorists have known that this was the most general form of this Hamiltonian for a long time. Okay. Anyway, so this was a cartoon that was used in my advertisement, and it just shows you, a way you might think of these pseudo-spin-a-half degrees of freedom, decorating a pyrochlore lattice. So right here you can see the Z components of pseudospin, and actually these are arranged in a spin ice type ground state because we have 2 of the magnetic dipoles with the blue lobe pointing in and 2 with the red lobe pointing in. So this is like 2 in, 2 out. And we can have, similar arrangements of the octupoles, right? But bear in mind that, I'm just showing you one component of the pseudospin on each of these sites. It's a cartoon, right? It's not meant to be a serious construct, really, but it just shows you how you might think about these things. Anyway, now I'm getting down to the low energy physics, which is where the condensed matter community typically starts to tune in. And I'm showing you, so before I showed you inelastic scattering on the scale of half an EV, now I'm showing you inelastic scattering about 100 times smaller in energy. It's 0.4 MeV. And actually, I'm showing you data that was taken on a single crystal, but I'm plotting the data as if it was taken on a polycrystalline material. So so neutron scattering and in general, the most general response to any measurement that we would make on a single crystal, you've got some quantity as a function of a scalar energy, but vector momentum transfer or vector momentum, right? So it's actually a 4-dimensional data set that you're looking at. So 4-dimensional data sets are hard to look at. So I'm just going to orientationally average over all of the vector momentum transfer. And it's going to let me look at all of the data at once, right, in a single 2-dimensional plot. And that's what you see here. Okay, and so this is energy versus the modulus of momentum. And actually, this is data that shows a temperature difference. So in this case, 60 millikelvin minus 10 Kelvin, and then 0.25 Kelvin minus 10 Kelvin, and so on. And we're going to identify the net magnetic scattering or the net scattering of interest by any region where there is more scattering at low temperatures than there is at high temperatures. So anything in red is what we're really interested in. And you can see that by the time you get to 3 Kelvin, there really isn't anything left. Okay, but as you go down below 1 Kelvin, you get this red region, which exists between 0 energy transfer and about 0.25 MeV. So one conclusion that we would have right away is that there is no temperature-dependent scattering at the elastic position at 0 energy transfer, which tells us that there's no static moment on the timescale of the neutron scattering measurement for any temperature above 60 millikelvin. And it also tells us that what's going on in this material is going on in this range of energy. So we're just going to integrate this up and then plot that net integration back onto a vector Q or a vector momentum transfer map. Okay, so it's going to show us a single crystal structure factor for the integral of this inelastic scattering, and it has this. This is the actual measurement, and it has this sort of snowflake-like pattern here. And you're probably not used to looking at these sorts of plots, but this is not what you see in an ordered material. In an ordered material, you see Bragg peaks, which are spots in reciprocal space. And this is a very extended diffuse scattering, which is typical of a very disordered material at 60 millikelvin. Okay, and actually our theory friends can calculate different expectations for exactly this type of experiment. So this would be what you expect for classical spin ice at 0 temperature. And there are these, again, you get a snowflake-like pattern with these very distinctive pinch points. Okay, so these pinch points are characteristic of so-called Coulomb correlations within classical spin ice. This is one version of quantum spin ice. I'm going to show you a better version of spin ice in calculation in just a moment, done by people here, done by Felix, who was here. I guess he's just left. Anyway, I'm going to show you his calculation soon. And but this calculation, it kind of looks like classical spin ice, but it's blobbier, which might be consistent with how you'd expect the quantum version of the problem to go. Anyway, I'm going to come back to that. This is another neutron scattering experiment, but a different one. The ones I showed you before were neutron spectroscopy. We had energy resolution. Here, we don't have energy resolution, but what we do have is a polarization dependence to a diffraction experiment. Okay, so we're doing two different diffraction experiments on the same material at the same time. So we're looking at, say, neutrons where we control the polarization of the spin. It's going to come in and it's going to scatter off the sample either with a spin flip or without a spin flip. And you get two quite different structure factors, which are shown here. And actually, what's interesting is that the non-spin flip structure factor actually still shows diffuse scattering, but the diffuse scattering is organized around the face-centered cubic zone boundaries that are appropriate to the pyrochlore lattice. Okay, so these are measurements that we did relatively recently on cerium zirconate. These are measurements that were done on the best example of classical spin ice from about 15 years ago. So classical spin ice, the quantum numbers are much bigger, the magnetic moments are much bigger, much easier experiment. You have much more intensity to work with. And this is really a very famous experiment because it shows these pinch points very, very well. And it also shows this diffuse scattering that goes around the zone boundaries of the FCC lattice. So the theorists know the general form of the Hamiltonian that's relevant for this system, and they've had a lot of time on their hands. So they've actually worked out, all of the possible phases that you can get from this problem, at least that are theoretically expected. Okay, and actually, there's quite a few phases here. But what I really want you to pay attention to is how much of this phase diagram is occupied by states that are labeled QSI. So QSI, this is a quantum disordered quantum spin ice. And there's actually 4 different flavors of it. There's something called a pi flux quantum spin ice. There's zero flux quantum spin ice. I can describe those to you if you like in say a question. I'm not gonna do so right now. Okay, but these are 2 different flavors of quantum spin ice, and they can be dominated either by the dipolar degrees of freedom or the octupolar degrees of freedom. So that gives you a total of 4 different quantum disordered quantum spin ices. And then around the periphery, there's a bunch of conventionally ordered states, either the dipoles order or the octupoles order. Okay, and so this is what's generally understood about the phases that are possible for this type of problem. Okay, so here we are. We're going back to our measurement. So this is the unpolarized neutron structure factor measurement that we published here in 2019. And we fast forward by 5 years, actually this year. And the group at Toronto, the theory group at Toronto, Felix Desroches and Youngback Kim, published this very nice phys.rev letter, which actually explores exactly what we measured, across that phase diagram. And what I'm showing you is expectations for this structure factor in the pi flux quantum spin ice versus the zero flux quantum spin ice. And you can already see that there's a remarkable resemblance between what we measure and what is expected within the pi flux quantum spin ice. Okay. And actually, they go further than that. They also, so this is the same calculation that I showed before. This is a calculation of the non-spin flip polarized diffraction that they would expect for the same set of parameters. And for the example where we had the good agreement with our unpolarized structure factor, we also have good agreement for this diffuse scattering along zone boundaries of the FCC lattice in the non-spin flip channel. So I think this by itself is very compelling evidence that what we're seeing in cerium zirconate is a pi flux quantum spin ice, okay, at 60 millikelvin. So I think this actually establishes it very well. There's still a whole bunch of open questions, but that part of it is established. So now, if we want to go further than this, actually, how much time do I have? Yeah.
0.
0, okay. So if we want to go further than this, then we've got to estimate the microscopic terms in the Hamiltonian. And we do that by getting together with another group of theorists, okay? And actually, so the data that is most useful to fit is heat capacity data. And they perform what's called a numerical link cluster calculation. It's kind of like high temperature series expansion. It's similar to that, if you know what that is. At any rate, it's a fit to the high temperature part of the heat capacity. And you can do that in zero field. You can do that in non-zero field. And the net result is that it allows us to estimate the microscopic terms in the Hamiltonian. And so if we have that, we can put those on our phase diagram. And we see that those indeed, so these are our 2 estimates. So one estimate is from zero magnetic field. The other is from finite magnetic field. This is a competing group working completely independently from us on different crystals. Everything's different. I'm sort of amazed how well it turns out. Anyway, I think there's very good agreement that it's a pi flux quantum spin ice, and it's close to the boundary between octupolar and dipolar dominated. Okay, and that's pretty much all I want to tell you about. I'll just finish with these 2 open questions. We're looking at quantum spin ices in dipole, octupole pyrochlores. Okay, so the open questions focus on 2 points. Okay, so one point is, can we observe the octupoles directly? Okay, so actually all the neutron scattering that I'm showing you, we feel that there's a very compelling case that there are, spin-1/2 degrees of freedom with both dipole and octupolar character, but the neutrons are primarily sensitive to the dipolar character. So the question is, can we observe the octupoles independently of the dipoles? And can we follow what the octupoles are doing independently of the dipoles? So that's an open question. And at the moment, there's conflicting results. And then the other one is all of the excitement associated with quantum spin ice is associated with the emergent quantum electrodynamics. And the thing that's really exotic about the emergent quantum electrodynamics is the emergent photon. And so is the emergent photon real? Okay. And can the emergent photon be observed directly? And again, at the moment, it's a developing story, so there isn't an answer to this. But I'm predicting that there will be in almost exactly 5 years, because I'm applying for my NSERC Discovery Grant now, and that's what I'm going to say. And anyway, these are the two really pressing questions. And with that, I can't put up all my collaborators' photos, so I just put up the most photogenic. And there's some of our relevant references here. So I apologize for running over time.